It is 2 o'clock in the morning on the 5th of February, 1980, in the High Magnetic Field Laboratory in Grenoble, and Klaus von Klitzing is sitting in front of an 18 Tesla magnet. Inside it is a silicon transistor, a hallbar cut from the technology that makes every logic chip, built for him by Gerhard Dorder at Siemens and Michael Pepper in Cambridge, cooled to around 1.5 Kelvin. He is turning a knob that changes how many electrons sit in the device, and a pen on a chart recorder is drawing the Hall voltage as he turns it. The pen ought to be drawing a slope, it is drawing a staircase. He works out one of the flat parts by hand in a notebook, and it comes to Planck's constant divided by the square of the electron charge divided by a whole number.
To as many figures as a chart recorder and a hand calculation give you at 2 in the morning. In the paper he published months later, it is a few parts in 1,000,000, and within a decade, a few parts in 10,000 million, and it does not care what the sample is made of. The Nobel Prize came in 1985, which, for an experiment nobody could yet account for, is quick. You said you wanted the spear and the spin and the donut settled at once on a voltmeter in a dirty piece of silicon. That is the voltmeter. The height of the plateau is Planck's constant over the electron charge squared, divided by a whole number, and the whole number is the total Berry curvature of the filled states over the Brillouin zone, divided by 2 pi, the integer we built out of a surface with no edges and an ambiguity about which side of a loop counts as the inside. Thouless, Kohmoto, Nightingale and Nijs wrote that down 2 years afterwards, and von Klitzing did not know any of it while the pen was moving.
None of that lands until I have the apparatus in my hands. What is the object he was measuring? What was the measurement supposed to give? And why is a slope the boring answer?
Edwin Hall, 1879, a graduate student at Johns Hopkins, asked whether a magnet pulls on a current or on the wire carrying it. Take a flat strip of conductor, run a current along it, put a magnetic field through the face. The moving charges feel a sideways force. They pile up on one edge, which builds a transverse electric field, which pushes back, and the pile-up stops when the two balance. So there is a steady voltage across the strip at right angles to the current. Divide it by the current, and you have what people call the Hall resistance. It is the standard way of counting carriers in a semiconductor, and has been since before anybody knew what a carrier was.
And it is proportional to the field and inversely proportional to how many carriers there are, because the more carriers you have, the less each one has to pile up before the fields balance. In an ordinary strip, it must also depend on the thickness, because a thicker slab has more carriers behind the same face.
In an ordinary strip, yes. And here is the first thing that makes von Klitzing's device peculiar. Squash the conductor until it is two-dimensional and the thickness drops out of the arithmetic altogether. The Hall resistance becomes the field divided by the areal density of electrons and their charge, and that combination is a resistance in ohms with no length anywhere in it. 2 dimensions is the one case where a Hall measurement hands you a pure resistance rather than a resistance per unit of something.
How do you make electrons two-dimensional in a piece of silicon? Because silicon is emphatically a 3-dimensional object.
You pull them against a wall. In the device von Klitzing had, a metal gate sits on an insulating oxide which sits on silicon. Put a positive voltage on the gate and it drags electrons up to the silicon side of the interface and holds them there, in a well a few nanometers deep. A well that narrow has widely spaced quantum levels across it, so at low temperature every electron is in the lowest one, and motion perpendicular to the interface is frozen out.
So it is not an approximation to a 2-dimensional gas, it is one. There is a direction in which the electrons have no available states at all at these temperatures. And the gate voltage is the knob he was turning, which means he was changing the number of electrons at fixed field, rather than sweeping the magnet.
Changing the number, which is the natural thing to sweep in that device. In gallium arsenide, which came later and became the workhorse, the density is fixed by growth, and you sweep the field instead. Either way, you are changing the ratio of electrons to field, and that ratio is the only variable in the problem.
So the prediction is a smooth curve. More electrons, less Hall resistance, in simple inverse proportion, with nothing interesting anywhere along it. Instead, the pen sits still for a while, jumps, and sits still again. How flat is flat?
Flatter than anything else in this course by a margin that is hard to convey. On the plateau, the Hall resistance is constant to parts in 10,000 million as you sweep, and the value it sits at contains no property of silicon whatsoever. Not the effective mass, not the mobility, not the impurity concentration, not the dimensions of the device, not the temperature.
Which is already the strangest sentence in 9 conversations, because every quantity we have computed so far has had the material's fingerprints on it. A transition temperature, an effective mass, a gap, a critical exponent that at least knew what dimension it was in. Let us guess it before you say it. What resistance can you even build without the material?
There is essentially one. A resistance is a voltage per current, which is an energy per charge per time. And if the only ingredients allowed are Planck's constant and the electron charge, the combination is forced. Planck's constant divided by the charge squared. Put the numbers in, and it is about 25,813 ohms. That is the whole plateau ladder. That number divided by 1, by 2, by 3, by 4. The second rung, at 12,906 ohms, is the one metrology laboratories actually use.
A resistance standard with no resistor in it, which sounds like a curiosity until you notice that a resistor is a manufactured object with a temperature coefficient and a drift, and this is not.
Since the 20th of May, 2019, Planck's constant and the electron charge are not measured quantities at all. They are defined, exactly, as part of the definition of the units, which makes Planck's constant over the charge squared an exact number of ohms, 25,812.8, and a long tail of decimals. The ohm is now realized by cooling a two-dimensional electron gas, putting it in a magnet and reading the plateau. It is called the von Klitzing constant, and calibration laboratories in every industrial country own one.
How was that ever tested, though? A number that comes out the same because everybody has agreed to define it that way is not an experiment.
By comparing devices with nothing in common and demanding the same answer. In 1991, Hartland and colleagues measured a plateau in a gallium arsenide heterostructure against a plateau in a silicon transistor. Different host, different effective mass, different crystal structure, different plateau index. And the two agreed to within a few parts in 10,000 million.
So the question this hour has to answer is not why the resistance is quantized, it is why it is quantized that well. A crystal at 1.5 Kelvin is a shaky, warm, impure object, and I would have said any property of it is good to 1% on a lucky day. 10 decimal places is not an improvement on that. It is a different kind of claim.
A different kind of claim, and it is worth more than the effect itself. Hold two facts side by side and let them bother you. The device is filthy. Von Klitzing's transistor had impurities everywhere, interface roughness, a mobility that would embarrass a modern grower. And the answer is the cleanest number anybody has ever pulled out of a solid. Those two facts are not in tension. They are the same fact.
What does a strong magnetic field do to a two-dimensional electron gas? I know what it does to one electron in free space, bends it into a circle, and I do not immediately see how a room full of circles becomes a staircase.
Start with the one electron and the circle, because everything follows from what makes that circle special. In 3 dimensions, an electron in a field spirals, circular motion across the field, free motion along it. In 2 dimensions, there is no along. The field is perpendicular to the plane, and every electron in the plane goes round, at a frequency set by the charge times the field over the mass. Circular motion at a fixed frequency is a harmonic oscillator wearing a rotation, and a harmonic oscillator has an evenly spaced ladder. So the kinetic energy of a 2-dimensional electron in a field is not a continuum. It is a ladder with rungs separated by Planck's constant over 2 pi times that cyclotron frequency. Landau, 1930.
A ladder in place of a band, then, which raises the obvious question, because a band held an enormous number of states, and a ladder rung is a single energy. The states cannot have vanished, so they must all have piled onto the rungs, and something has to say how many fit on each.
Guess it the way we have been guessing all course. What could the number possibly depend on? You have Planck's constant, the electron charge in the field. Out of those you can build exactly one area, Planck's constant divided by the charge in the field, and that is the area through which the flux equals Planck's constant over the charge. 1 flux quantum. So the number of states per rung per unit area is 1 over that area.
That is a formula, and I cannot see it. What is the picture?
Rule the plane into tiles, each chosen so that exactly 1 flux quantum threads it. Every Landau rung holds exactly 1 state per tile. That is the whole counting, and it is worth noticing how little went into it. No lattice, no bandwidth, no chemistry, the field and 2 constants, and the answer. The flux quantum appearing here is Planck's constant over 1 electron charge, because 1 electron is what is being counted. The superconducting ring divided it by 2, and that 2 was the evidence for pairing. Same constant, different denominator, and the denominator is always telling you what the carrier is.
And it says something outrageous, which is that the number of available states is fixed by the magnet and by nothing about the material at all. Turn the field up and the tiles shrink, so each rung swallows more electrons. Is a tile a real size, or is this astronomically small and therefore a bookkeeping device?
A real size. The tile is about 64 nanometers across at 1 Tesla. The length the wave functions themselves care about, the square root of Planck's constant over 2 pi divided by charge times field, is about 26. Both shrink as the square root of the field, so at von Klitzing's 18 Tesla, it is 15 nanometers and 6 tens of atoms. And the number of states works out at about 2.4 times 10 to the 10th per square centimeter for every Tesla, against a typical 2-dimensional density of a few times 10 to the 11th.
So at 10 or 20 Tesla, you have pushed nearly everybody down into the bottom rung or 2, which is presumably why these experiments need the magnets they need. And the only variable left is the ratio, electrons per tile, which the gate moves one way and the field moves the other.
The filling factor, and now the crucial case. Suppose it is exactly a whole number, say 3. 3 rungs completely full, the 4th completely empty, and to excite anything at all, you must lift an electron a whole rung. There is a gap. Nothing can absorb a small amount of energy, nothing can be nudged, nothing can dissipate, and the longitudinal resistance, the ordinary one, measured along the current, drops to 0.
How big is that gap in temperature, so I know whether 1.5 Kelvin is comfortable or heroic?
Comfortable. In gallium arsenide, the effective mass is about a 15th of the free electron mass, which multiplies the rung spacing by 15, and at 10 Tesla, the rungs sit tens of milli-electron volts apart. In temperature that is well over 100 Kelvin, against an experiment run below 1. In silicon, the mass is heavier and the gap smaller, which is why von Klitzing needed 18 Tesla rather than 5. The ratio of gap to temperature is enormous either way, and that is why nothing is smeared.
There is something wrong with the story as told, and it is not a quibble. A whole number of electrons per flux quantum is one exact condition. Fix the density and it happens at one exact field. So, the special state ought to be a knife edge that no experiment could sit on. And what von Klitzing saw was a flat region wide enough to draw with a pen.
You have found the hole, and it is the right one. In a perfectly clean sample, there is no plateau. Sweep the field through the special value, and the Hall resistance passes through the ideal number exactly, at one point, and carries straight on. A plateau of zero width. The staircase does not exist.
Then the plateau is not a property of the ideal system at all. It is made by the imperfections, by the very thing I would have put in the error budget.
Made by the imperfections, and this is the least intuitive thing in the hour, so we will go slowly. Put disorder in, impurities, interface roughness, a random potential landscape with hills and valleys of a few milli-electron volts. Each Landau rung, which was a single sharp energy, spreads into a band, because an electron sitting in a valley has slightly lower energy than one on a hill. Now ask what those spread-out states look like in space. A state well down in the tail of the band is one trapped in a valley, circling a closed contour of the landscape, going round and getting nowhere. It is localized, and it carries no current from one end of the sample to the other, ever.
And in the middle of the band, the contours must be different, because a contour halfway up the landscape is the one that snakes between the hills, instead of ringing one of them.
Which is exactly it. Near the center of each broadened rung, there is a narrow set of energies where the contours percolate, where a path connects one side of the sample to the other, and those states carry. So each Landau band is a sandwich, localized in both tails, extended in a thin slice at the middle.
I can see how that gives width. Sweep the field, and the Fermi level walks up through a band. While it is in the tail states, the electrons you add go straight into traps and change nothing about transport, because the extended states below are still all full, and the ones above still empty. So the Hall resistance sits still, and only moves when the Fermi level crosses that thin, extended slice. Dirtier sample, fatter tails, wider plateau.
The cleanest sample in the world has the narrowest, and in the limit of no disorder it has none, which is a thing to say slowly to anybody who thinks the quantum Hall effect is a triumph of sample purity.
I have had the role of disorder upside down all my life then. But this leaves a worse problem. If a large fraction of the electrons are sitting in traps carrying nothing, the current is being carried by fewer electrons than I counted, and the Hall resistance was the field divided by the density of carriers. Take carriers out of that and the resistance must come out too high by whatever fraction is trapped. So every sample should read a slightly different plateau, close to the ideal value, wrong in the fourth decimal place, and wrong by an amount that tells you how filthy it is.
That is a clean argument, and it is false, and the way it fails is the heart of the subject. Planck did the calculation in 1981 for the simplest case anybody could set up. One delta function impurity in an otherwise perfect Landau level. It creates one localized state which carries nothing, exactly as you say, and the remaining extended states in that level carry more than they did before. More by precisely the amount the trapped one is not carrying. The total is unchanged. Not approximately unchanged, unchanged.
Why would they do that? The surviving electrons have no way of knowing that one of their number has been arrested, and there is no force in the problem that tells them to take up the slack.
No way of knowing, and no mechanism in that calculation that makes them compensate. It falls out of the arithmetic, which tells you the answer is being controlled by something the calculation does not name, because a conspiracy that exact is not a coincidence you can accept twice. And it gets worse when you notice the compensation has to survive not one impurity, but 10 to the 12th of them, all different, in a sample nobody characterized. The theory owed an explanation of why nothing in the sample can affect the answer at all.
Where does the integer come from? We spent an entire hour on Berry curvature, and I would rather watch it earn its keep here than take the result on trust.
Every piece is already on the table. First piece, an electron in a band, pushed by an electric field, does not simply move along the band's slope. It acquires a second velocity, at right angles to the push, equal to the rate of change of crystal momentum crossed into the Berry curvature at the electron's own momentum. The anomalous velocity, and it is the reason a Hall current can exist at all without anybody invoking a magnetic force on a moving charge.
A sideways velocity for every occupied state, which I add up to get a current. And if the band is completely full and separated from the next by a gap, the sum runs over every state in the zone. So it is not a sum anymore, it is the integral of the Berry curvature over the whole Brillouin zone.
Times the charge squared over Planck's constant. One charge to feel the field, one to carry the current. The 2 pi is the same count you already did for the tiles. Fitting waves into a box gives you a fixed number of momentum states per unit area, and dividing by it is what turns your sum over occupied states into an integral. So the Hall conductance is a pure number times a combination of fundamental constants, and the pure number is an integral of curvature.
What is the Chern number of one filled Landau rung?
1, which is why the number of filled rungs and the plateau index are the same integer. You count it as full rungs from inside, and in a moment you will count it as one-way wires from outside, and the two counts are forced to agree.
And the third piece is the donut, which I can do without help. The zone has no boundary because two crystal momenta differing by a reciprocal lattice vector are one state and not two, so the faces are glued to their opposites, and in 2 dimensions, the result is a torus. Total curvature over a closed surface is forced to be an exact multiple of 2 pi, because a loop drawn on it cannot know which of the 2 regions it fences off I am calling the inside.
Both answers have to be the same phase, so they may differ only by whole turns. Divide by 2 pi and you have an integer.
Can you put the whole thing in one sentence, with the physical job of each part named? That is the result of the hour, and I need it whole rather than in 3 pieces.
The Hall conductance of a filled band is a whole number times the electron charge squared over Planck's constant. The charge squared over Planck's constant is the natural unit of conductance for a single quantum channel, not a fitted scale, but what falls out of the constants alone, and the reciprocal of the resistance von Klitzing measured. The whole number is the total Berry curvature over the Brillouin zone divided by 2 pi, the number of times the internal phase of the wave function wins as you cover the zone once. It is called a Chern number, after the geometer Xing-Shen Chern, whose invariants these are. Barry Simon made that identification in 1983, 16 months after Thouless and his collaborators found the integers without knowing what kind of object they had found. And notice what is not in that sentence. No mass, no density, no scattering time, no sample, no material. The only thing the crystal contributed was a band and a gap.
The derivation I now have. The reason I do not. Why is it precise?
Because the answer is an integer, and there is no such thing as an integer that is slightly wrong. Take the real device, impure, warm, finite, with a random landscape and a bent edge, and a contact soldered on badly. All of that is a deformation of the Hamiltonian. Deform continuously, and the total curvature must move continuously. And the total curvature is pinned to multiples of 2 pi at every instant. A continuously varying quantity that is only allowed on a discrete set does not vary. It sits.
So the precision is not a matter of the corrections being small. Small corrections would still be corrections, and they would show up in the 9th decimal place and differ between samples. This is the statement that there is nowhere for a correction to go, because every question I could ask about the device is a question about a smooth deformation.
Nothing to grip, and that is a genuinely different kind of statement from anything else in this course. When we computed a heat capacity or a critical exponent, being close was an achievement, and the error bar was a real object with physics in it. Here the error bar has been abolished by the structure of the answer, and what is left is not the accuracy of the theory, but the accuracy of your voltmeter.
What is the escape, though? Because the staircase does have steps in it, so the integer does change, and a quantity that cannot change is no use for describing a staircase.
The escape is the premise. The argument assumed a gap, a full band, an empty band, nothing at the Fermi level anywhere in the zone. Close that gap somewhere, and the integral stops being defined at the moment of closing, and on the far side it can be a different whole number. There is no other route. You cannot walk an integer from 3 to 4. You can only break the thing that made it an integer in the first place.
And that is the step. The Fermi level crosses the extended states in the middle of a Landau band. The bulk conducts for a moment, the integer jumps, and the plateau resumes one rung down, which also explains the other curve. The longitudinal resistance is 0 on the plateaus and spikes at the steps, because the only moment the bulk conducts is the moment the invariant is changing.
The two curves are telling you the same thing, and it is a good consistency check to carry. Now I owe you a warning about what I just proved, because I proved it for the wrong system. That argument assumes a crystal with bands and a filled Brillouin zone. Von Klitzing's sample is disordered, the whole plateau depends on disorder, and a disordered sample has no crystal momentum and no Brillouin zone.
So the derivation applies to the clean system, which is exactly the system that has no plateau. And the plateau belongs to the dirty system, which has no zone. That is not a small gap in the argument.
It is not, and the repair is new, Thouless and Wu, 1985. If the sample will not supply a torus, impose one. Put the system in a box and demand that the wave function return to itself, up to a phase, when you go round in each of the two directions. Those two phases are yours to choose. The space of choices is a torus, and the Hall conductance over that torus is a Chern number again. The invariant survives disorder, and it survives interactions, because nothing in the construction assumed either was absent.
What is the cost of that repair? I am suspicious of a torus I put in by hand, rather than one the crystal handed me.
The cost is real. The torus of boundary phases is not something you can point at in the laboratory. It is a family of Hamiltonians you could have written down, not a structure in the sample. And the argument gives the invariant for the conductance averaged over those phases, with a separate step needed to show that a large sample does not care about the average.
There is another route to this, isn't there? Lachlan had an argument before any of it, and I remember it being the one people actually keep in their heads.
A year before, 1981, and it is the one to carry if you keep only one. Roll the Hall bar into a cylinder so the current goes round the circumference and the Hall voltage is between the two rims. Now thread a magnetic flux slowly up the axis, in the region where the electrons are not. They never touch it. The situation Aharonov and Bohm set up, and they respond to it anyway. Increase the flux by exactly one flux quantum, and the Hamiltonian returns to itself. You can gauge the added flux away entirely. So the system must come back to a state it could have started in.
It comes back to itself, but not necessarily to the same state, because the states could have been shuffled amongst themselves while the flux was going in. And in an insulating bulk with two conducting rims, The only shuffle available is that some electrons have been carried from one rim to the other.
Some whole number of electrons, because you cannot deliver a fraction of an electron to a metal contact. So the work done is that number times the charge times the Hall voltage. The current is the work per unit of flux, and 1 unit of flux is Planck's constant over the charge. Put those together, and the Hall conductance is a whole number of conductance quanta.
And now the integer is not an abstraction at all. It is a count of electrons that physically moved across the sample when you threaded 1 quantum of flux, and there is no arguing with a count. What did that argument need that I should not forget?
An insulating bulk, so nothing can leak between the rims except by the pumping. In a clean sample at exact filling, that insulation is the Landau gap. In a real sample away from exact filling, it is the localized states, the Fermi level sitting in a sea of trapped electrons that cannot conduct. So disorder is not something the argument tolerates, it is a premise of it.
I want to push on the word insulating, because you have now said twice that the bulk does not conduct while the sample is passing a current. Both cannot be true of the same region.
They are true of different regions, and the difference is forced on us by the integer. Stand inside the sample, the invariant is 3. Stand outside, in the vacuum, the invariant is 0, because there is nothing out there to have curvature. The invariant is a whole number, and it cannot change by degrees. So somewhere on the way from inside to outside, it changes by 3, and the only way it is permitted to change at all is for the gap to close.
So the gap closes at the boundary, which means there are states at the Fermi level there, which means the boundary conducts whatever the interior is doing, and I have derived the existence of a metal on the skin of the sample without ever going near the skin.
Without going near it. That is bulk boundary correspondence, and it is my favorite argument in physics, because the whole content of it concerns the inside, and the whole conclusion concerns the outside. You compute a number from the filled states deep in the material, where nothing at all is happening, and you have proved that the surface must be a conductor.
Is there a picture of the edge state that does not require any of this? Something a physicist in the 1930s could have drawn on the back of an envelope.
A very good one, and nearly as old. In the bulk, an electron in a strong field goes round a small circle and gets nowhere. That is, the localization the field imposes all by itself. Near the wall, the circle is interrupted. The electron completes part of an arc, hits the boundary, bounces, starts a new arc. A skipping orbit. And because every circle turns the same way, every bounce advances the electron in the same direction along the wall.
And on the far edge, the same rotation sense carries it the other way, so the two sides of the sample carry current in opposite directions, and each side carries it one way only. That one-wayness is the property that matters, isn't it, rather than the mere existence of states at the boundary?
That is the whole property. Call it chirality. Put an impurity right next to the edge channel and ask what it can do. Scatter the electron forwards, which changes nothing because forwards is the only place to go. To turn it round, the impurity would have to put it into a backward-moving state, and the only backward-moving states are on the other side of the sample, a millimeter away, across an insulating bulk. That matrix element is not small, it is astronomically small. So an edge channel transmits perfectly, over any distance, through any amount of dirt. Halperin saw this in 1982. Buttiker turned it into a transport theory in 1988, and his title is a fair summary. Absence of backscattering in the quantum Hall effect.
A perfect one-way wire carries exactly the charge squared over Planck's constant. One channel, one spin. And there is one such wire for each filled Landau level. So the count comes out at the same integer from the outside that the curvature gave from the inside.
The same integer approached from opposite directions, because it is the same integer. Which means that on the plateau, The current flows entirely along the two edges, and the bulk of the sample carries none of it.
A hall bar a millimetre wide, with two threads of current running down the sides, a few tens of nanometers in from the boundary, and everything in between doing nothing at all. That is a far more concrete picture of a working conductor than I expected to be handed.
It is more concrete than the physics supports, and the sentence I said was wrong. Where the current actually flows in a hall bar is not determined by any of this. Experiments that image the current distribution have found it spread through the bulk in some samples and hugging the edges in others, and the answer depends on the contacts, the geometry, the density profile, how the thing was cooled. There is a long argument about it that is not settled and does not need to be. What the topology guarantees is that gapless modes must exist at the boundary. It does not guarantee that those modes are carrying your current, and the quantized answer comes out the same either way, which is the point rather than an embarrassment. A quantity that depended on where the current chose to flow would not be good to 10 decimal places.
So the edge count is a legitimate way of getting the number, and an exact statement about which states exist, and not a photograph. The existence claim I hold tightly, and the current path claim loosely.
Tightly and loosely, in that order. And keep one more thing from the edge picture, because it is the piece that travels furthest. A one-way conductor is not something you can build out of ordinary components. Any wire you have ever made carries current both ways, and the reason is that its states come in pairs moving in opposite directions. Here they do not, and they cannot, because the number that forces them into existence is different on the two sides of the boundary. That is the object every topological material is chasing.
The integer story sounds closed. It is derived, it is measured, it is a unit of resistance in every national laboratory. What went wrong?
1982, at the Francis Bitter Magnet Laboratory. Daniel Tsui and Horst Stormer, with samples grown by Arthur Gossard at Bell Labs. Gallium arsenide with the donors deliberately set back from the channel so the electrons see far less scattering than in silicon. Very high mobility, very low temperature, very high field, pushed past the last integer into the regime where only a fraction of the lowest Landau level is occupied. They were looking for an electron crystal. Wigner had predicted decades earlier that electrons with enough room would freeze. What they found was another plateau, at 1/3.
A plateau at 1/3 of a filled level. What is that a statement about? Go back to the tiles. 1/3 filling means 1 electron for every 3 flux quanta. So 2/3 of the bottom rung is empty, and every one of those states has exactly the same energy. There is no gap for the plateau to be a consequence of.
There is no gap, and that is precisely the catastrophe. The number of ways of choosing which third of the states are occupied is astronomically large, and every single choice costs the same kinetic energy. Nothing in the single particle problem distinguishes any of them, and therefore nothing can produce a gap. And yet the Hall resistance sits on a plateau, which means there is a gap.
And the only ingredient left in the problem is that the electrons repel each other, which everywhere else in this course has been a correction to something, and here has nothing to be a correction to.
Notice the position it has been put in. Everywhere else the interaction dressed a quasi-particle, or shifted a transition temperature, or produced a weak pairing on top of a Fermi sea. Here the kinetic energy is a constant across the entire space of candidate states, so it cannot decide anything, and the interaction is not a perturbation on the answer. It is the whole of the answer. Degenerate perturbation theory with a macroscopic degeneracy and no small parameter anywhere, which as a technical matter is the worst position many body physics ever finds itself in.
What would you have guessed the electrons do? I would say crystallize, and so would Wigner, and so did the people who found it.
I would have said crystallize too, and their own paper offers a Wigner solid or a charge density wave as the candidate. It is wrong, And it is wrong in a way worth stating, because a crystal is not merely a different answer, it gives a different measurement. A crystal breaks translational symmetry and has a gapless mode, and disorder pins it. So what you get is an insulator with no plateau anywhere, which is exactly what is seen much further down, below about 1/5 filling. What the system does at 1/3 instead is form a liquid, uniform, with no broken symmetry and nothing chosen, that nevertheless has a gap.
A liquid with a gap, which 4 conversations on broken symmetry did not prepare me for in the slightest. How does anybody even write down a wave function for that? There is no small parameter, no mean field, no obvious variational family to minimize over.
Robert Laughlin guessed. 1983, and the guess is short enough to say out loud. Label each electron's position in the plane by a complex number. The wave function is a product over every pair of electrons of the difference between their 2 positions. That whole product raised to the power 3 multiplied by a Gaussian envelope that keeps everybody inside the droplet.
What is each piece of that doing physically? A product of differences raised to a power is a shape, and I want the reason.
The difference between 2 positions vanishes when those 2 electrons sit on top of each other, so the product vanishes whenever any 2 coincide. Any fermionic wave function does that once. That is Pauli, and no more. Cubing it means the wave function vanishes to 3rd order as 2 electrons approach. It goes to 0 far faster and from much further away than anti-symmetry requires. Each electron drills a hole in the probability cloud around itself that is 3 times deeper than the law demands.
Which is exactly what a repulsion would pay for, if it had a say. And the Gaussian is nothing but the lowest Landau level, the envelope that says this state lives on the bottom rung and nowhere else.
The remarkable part is the exponent, because it does a second job for free. The highest power of any single electron's coordinate controls how far out the droplet spreads for a given number of electrons. Raise the exponent and you spread the same electrons over more area. Work it through for the exponent 3, and the droplet contains exactly 3 flux quanta per electron.
So one number sets both how hard the electrons avoid each other and what density the state exists at, which is a very strong constraint on the theory rather than a free parameter. And it must be the reason the fractions come in the pattern they do, because the exponent has to be odd, or the whole thing is not antisymmetric.
Odd. So the construction gives 1/3, 1/5, 1/7, and nothing else whatever. Which is a bold thing to get out of a guess. It says where you may look and where you will find nothing.
Is there any argument that the guess is right, or is it right because it agrees with the experiment? Those are very different situations, and I would like to know which one we are in.
2 arguments and 1 gap. The first is Laughlin's own. Square the modulus of that wave function and you get, exactly, the Boltzmann weight of a completely different classical problem. A 2-dimensional gas of charges repelling logarithmically in a uniform neutralizing background. That system was already understood. At the relevant coupling, it is a uniform, incompressible liquid that screens perfectly. So the quantum state inherits uniformity and incompressibility from a classical calculation somebody else had already finished.
And the second argument is presumably a computer, because at some point somebody must have just solved a small version of this exactly.
Put a handful of electrons on a sphere or a torus, write down the full Coulomb Hamiltonian, diagonalize it exactly, and overlap the true ground state with Laughlin's guess. For a dozen electrons, the overlap is around 99%, in a space of enormous dimension where a random guess would give essentially nothing. The gap is that neither of those is a derivation. Nobody has produced that wave function from the Coulomb Hamiltonian by a controlled argument. It is a guess that turned out to be very nearly the answer, and it remains a guess.
What does the liquid do when you disturb it? For the integer case, I know the answer. Lift an electron, a rung. and here there is no rung to lift it to.
Take one flux quantum and push it slowly through the liquid at some point. The classical plasma analogy tells you what happens. Charge is pushed away from the puncture, and the amount is set by the density you already know. 1 electron for every 3 flux quanta, so pushing one more flux quantum through displaces a third of an electron. So the elementary excitation of this state is a localized object carrying a third of the charge of an electron.
In what sense is that a real statement rather than an accounting convention? Nothing has been cut into 3, and the electron is not the sort of object that has thirds.
Nothing has been cut. The electron is intact and indivisible everywhere in this story. What carries the third is a rearrangement of the whole liquid whose charge deficit is concentrated in a region a few tens of nanometers across. Integrate the missing charge density over that region and you get a third. It is the same logic that lets a hole in a semiconductor carry a positive charge without any positive particle being present anywhere in the crystal.
Except that a hole carries a whole charge, and this does not, which is the entire novelty. Can I measure it? Because a rearrangement I cannot weigh is not obviously better than an accounting convention.
Measured in 1997 by 2 groups independently, using an idea out of vacuum tube engineering. Current is not smooth, it is delivered in lumps, and a stream of lumps is noisy. Schottky worked out in 1918 that the noise power of such a stream is proportional to the current times the charge of one lump. So the noise measures the graininess. Make a narrow constriction in the 2-dimensional gas, a gate that pinches the liquid so excitations have to tunnel across a small insulating neck one at a time, and measure the noise of what gets through.
And the graininess comes out at a third of what it should, which is a direct reading of the charge of whatever is tunneling, rather than an inference from a plateau.
Saminadaya, Glatley and colleagues at Saclay, and De Picciotto, Resnikov, Heiblum and colleagues at the Weizmann Institute in the same year from opposite ends of the same idea. In 2008, they did it at the state at 2.5 and got a quarter. The year after the first of those measurements, Tsui and Stormer for finding the plateau and Laughlin for saying what was underneath it shared the 1998 prize.
What are these things statistically? An excitation with a third of a charge is not an electron, so I have no right to assume it is a fermion, and I cannot think what else is on the menu.
In 3 dimensions, there is nothing else on the menu, and that is a theorem rather than a convention. Take 2 identical particles and swap them. Do it twice, and you are back where you started. In 3 dimensions, the double swap can be continuously untangled. The path of one particle looping round the other can be lifted out of the plane and shrunk to nothing. So the square of the exchange phase must be 1, which leaves +1 and -1. Bosons and fermions, and no third option.
And in 2 dimensions, there is no out of the plane to lift the loop into, so the loop cannot be shrunk without passing through the other particle. The double exchange is not the identity anymore, and the phase is not pinned to + or -1.
It can be anything. Lehnes and Meerheim published that in 1977, purely as a question about what quantum mechanics permits in 2 dimensions, with no system in mind at all. Wilczek gave them their name in 1982, anyons, because the phase can be any phase.
And somebody then went and checked whether Laughlin's quasi-particles are 1, which is the sort of question that only becomes askable once the excitations are agreed to exist.
Arovas, Schrieffer and Wilczek, 1984. Take one quasi-particle slowly round another in a closed loop and compute the phase the wave function accumulates. It is a Berry phase, the same object as the spear coming home turned, with the parameter now being the position of the quasi-particle you are dragging. The answer for the 1/3 state is 2π/3, not 0 and not pi.
How long did it take to see that in an experiment? because a phase of 2 pi over 3 is a much harder thing to catch than a charge.
36 years, and it arrived twice in the same year. In 2020, a group at Purdue built an interferometer out of the edge channels of a 1/3 state and watched the interference phase jump in discrete steps of 2 pi over 3 as quasi-particles entered the loop one at a time. In the same year, a group in Paris collided two dilute beams of anyons at a beam splitter and read the statistics off the correlations between the outgoing currents.
I want to be careful about what that establishes because braiding gets talked about as though it were already a technology, and I do not think this experiment says that.
It does not. What is established is that exchanging two of these excitations multiplies the state by a phase that is neither 1 nor -1, which was the open question and is now closed. What is not established is anything computational. The phase for the 1/3 state is an ordinary number, so exchanging two of them in one order gives the same result as the other order. To compute with braiding, you need excitations for which the order matters, where the exchange operations are matrices that do not commute, and that is a different claim about a different state.
What is fundamentally different about the fractional case? I would like to be able to defend the distinction to somebody who thinks it is the integer effect at a smaller number.
3 differences, and the first decides the others. In the integer case, the ground state is a filled band, a single Slater determinant, the state you would write down for electrons that never speak to each other. Switch the interactions off entirely, and the effect survives untouched. The topology lives in the band structure, which is a single particle object. In the fractional case, there is no band to fill and no determinant to write. The degeneracy is macroscopic, and the gap is manufactured by the repulsion. Switch the interaction off, and the state does not weaken. It ceases to exist.
Which is a difference in what the phenomenon is made of, not in how big the number is. Second,
the excitations. The integer effect has electrons and holes, carrying the charge they always had and obeying the statistics they always obeyed. The fractional effect has objects carrying a third of a charge and a braiding phase that is forbidden in 3 dimensions. Nothing in the integer case fractionalizes anything.
And the third? You said the integer case keeps its topology in the band structure. If the fractional case has no band, that invariant has to live somewhere else, and I would like to know where.
The ground state is not unique, and how many there are depends on the shape of the space the electrons live on. Put the 1/3 state on a sphere, and there is one ground state. Put it on a torus, and there are 3, exactly degenerate, and no measurement made inside any small region of the sample can tell you which of the 3 you are in. That is not a Chern number of a band. It is a property of the many-body state that the integer effect simply does not have. Xiaogang Wen named the general idea topological order, and this is its cleanest example.
Is the sequence of fractions understood, or is each one its own separate guess? Because 1/3 and 1/5 I can get from the exponent, and 2/5 I cannot.
Largely organized by one idea. Jainendra Jain, 1989, attach 2 flux quanta to each electron and treat the result as a new particle, a composite fermion. The attached flux points against the applied field, so composite fermions see a much weaker effective field than electrons do, and at filling 1/3 the cancellation leaves them seeing exactly the field appropriate to filling one of their own Landau levels. The fractional effect of electrons becomes the integer effect of composite fermions. Fill 2 composite levels and you get 2/5. 3 gives 3/7. Essentially, the entire observed sequence falls out.
That sounds like a complete answer, which makes me suspicious of the way it is being sold to me. Where is the join?
Flux attachment is a construction, not a derivation. Nobody obtains the composite fermion from the Coulomb Hamiltonian by a controlled approximation. You write the transformation down, compute with it, and find it works extraordinarily well against experiment and against exact numerics. The same is true of the effective field theory built on it. A framework that predicts correctly and is not derived is a different sort of object from the integer case, where the answer is a theorem.
Where does it stop working altogether?
At even denominators. Willett and colleagues found a plateau at filling 2.5 in 1987, and an even denominator is forbidden by the odd exponent argument and does not sit anywhere in Jane's sequence. The leading proposal is that the composite fermions there pair up, a superconductor made of composite fermions, and that the excitations of the paired state are non-abelian, the case where the order of braiding matters, and the one that would actually make a topological quantum computer. Which candidate state it is has been argued about for over 30 years. A measurement of the thermal conductance of the edge in 2018 came out at a value that does not match what the numerical work favors, and the disagreement has not been resolved.
So the position on the fractional effect is what, exactly, if I have to state it in one breath to somebody who will hold me to it?
The phenomena are solid, and the theory is not derived. The plateaus are there, the fractional charge is measured, the anionic phase is measured, and the wave functions we use are trial states that agree with small system numerics to a couple of decimal places. Nobody has a controlled route from the microscopic Hamiltonian to any of it. These are the best studied, strongly correlated states we possess, and they are not solved.
What else does the topology fail to deliver? I notice that everything you have quantized is a conductance, and a device has rather more numbers in it than that.
It delivers the conductance and nothing else. The size of the gap is a Coulomb energy and depends on the material, the density, the width of the well, the disorder. The width of the plateau depends on the disorder in a way nobody computes from first principles. The temperature at which the whole thing washes out is non-universal. Which fractions appear in which sample is a question about competition between candidate states, settled numerically, sample by sample.
One number to 10 decimal places, and everything else measured. That is a much narrower claim than the reputation suggests.
Somebody shows you a flat region in a transport measurement and tells you it is topological. What would make you disbelieve them?
3 things, and I would want all 3. The height, a whole number times the charge squared over Planck's constant, with no property of the material in it, and it must not move when they hand me a different sample of a different substance, with a different amount of dirt. If it drifts with the growth run, it is not an invariant. The edge, if the interior carries a whole number and the vacuum carries 0, the number cannot get from one to the other without the gap closing on the way out, so there must be one-way conducting states around an insulating region. A bulk invariant with an insulating boundary means one of the 2 claims is wrong. And the way it changes, it must not creep. It must sit and jump and sit, with the jump coinciding with the bulk conducting.
And if they told you the number on the plateau was 1/3 rather than 3.
Then almost none of that reasoning is available, and the questions change altogether. The gap cannot be a Landau gap because there is not one at that filling, so it has to be built by the repulsion, and I would want to know what happens as the interaction is weakened, because the state should die rather than shrink. I would ask what charge tunnels through a constriction and expect a third. And I would ask how many ground states there are on a donut, because the integer case has 1, and this should have 3.
Which is the distinction, and it took the field the better part of a decade to see that it was a distinction rather than a complication.
There is something about this hour that will not leave me alone, and it is not the physics, it is the hardware. Everything we have discussed needed 18 Tesla, a magnet the size of a small car, a helium plant, a building with its own power feed. And what the magnet is finally doing is supplying Berry curvature that does not cancel when you add it over the zone, because it breaks time reversal symmetry, and time reversal was the thing forcing the curvature at opposite momenta to be equal and opposite. Is a room-sized magnet really the only way to break a symmetry?
It is not, and that is the next hour. A crystal can break time reversal internally with magnetism of its own and give you an integer with no external field at all. Duncan Haldane wrote down a model doing exactly that in 1988 on a honeycomb lattice with no net flux anywhere, and it took people 25 years to build one. The bigger prize is stranger. Keep time reversal symmetry. Keep the curvature cancelling in the total so that the churn number is zero and every argument we made today gives you nothing whatever. And then ask whether the cancellation itself can be arranged in two inequivalent ways. Whether there is still something to count, not how many, but whether the arrangement is odd or even. The ingredient is not magnetism. It is the coupling between an electron's spin and its own motion, which every heavy atom has for free.
An insulator with a metallic skin, and nothing in the room to switch off. If that works, the plateau stops being an achievement of a magnet laboratory and becomes a property of a material sitting on a bench.